Okay, so what I'd like to do is just go through one of the examples from the example sheet to give you an idea of how I would go about solving it. So the idea being that you can't get everything from the solutions, the printed solutions, because you need to see what kind of thought processes go on before you can actually get to the final answer. So the one I wanted to look at was question 23, which just asks you to show that this sequence here tends to a limit. Now before we can do that, what we have to do is remind ourselves what that actually means. So it's completely meaningless unless we know what the definition of tends to a limit is. So we have to go back to the definition, which is why I've written it up here. So we have to show, well, what does it mean for a sequence xn to tend to a limit? So xn tends to a limit x if for every epsilon greater than 0, every positive number, possibly a very, very small number, there is a big N such that the difference between xn and the limit, so the nth term and the limit, is very small, so less than epsilon, whenever n is bigger than big N, whenever this one is after the big N term. So if you give me a small number, I've got to find a point in the sequence after which all the terms in the sequence are less than epsilon away from this next here. Okay, so how are we going to do it? So first thing to do, so let's just do our rough work first, is, so if we just let's just give this a name, let xn be n pi plus sine n all over n, and we're going to have to guess the limit. So we're going to guess that xn tends to what? Well, you can, there's a couple of ways of doing this. You could just type big numbers into your calculator and see what seems to happen, or we can just try and think about it. So if this n will cancel with this n, so we get pi plus sine n over n. N is going to get very big. Sine n is always going to stay sort of between plus and minus 1. So it looks like this term is going to become negligible, and so the whole thing is eventually just going to tend to pi. Okay. So that's the first thing to do, is just guess what the limit is. So then what do? Well, we have to show that given any epsilon, so let epsilon be some positive number, possibly like a millionth or a trillionth or something. So we have to find some n so that this is true. So let's just consider this condition. So then xn minus pi is going to be equal to the modulus of n pi plus sine n all over n minus pi. Pi is going to cancel with that, so that's going to leave us with sine. So the modulus of sine n over modulus of n, but this is less than or equal to 1 over n. So this is because the modulus of sine n is always between plus 1 and minus 1, so the modulus is always less than or equal to 1. So the difference between xn and pi is always less than or equal to 1 over n. Now we wanted to find terms where it's less than epsilon. Okay, so as long as we make sure that 1 over n is less than epsilon, then this is going to be less than epsilon. So this is less than epsilon, provided that n is bigger than 1 over epsilon. So let me just run through that again. So just say that another way. So I could have said it that way. Let me just try saying it another way. So it suffices for 1 over n to be less than epsilon, i.e. n is bigger than 1 over epsilon, because if that's true, then mod xn minus pi is going to be less than epsilon. So this is This is the thing we were looking for. We were looking for some number such that when little n is bigger than that number, then the difference between the terms in our sequence and the limit is less than epsilon. So this is the bit we've got to remember from our rough work here. So now we can obliterate our rough work, but just remember that. So we're going to take that. But so we want little n to be bigger than 1 over epsilon for this to be true, and that's supposed to be the job played by big N here. This is going to be the point after which this inequality is true, so we want to take big N to be the reciprocal of epsilon. So if epsilon was a millionth, we'd take N to be, big N to be a million. So what we needed to remember was N was bigger than 1 over epsilon. So I've now obliterated the rough work, and now I can start the proof properly. And the only thing I remembered from the rough work was that n is bigger than epsilon. Okay, so now the proof goes as follows. So we need to show that whenever you give me an epsilon, a positive epsilon, so let epsilon be bigger than 0, now I need to show that for every epsilon you give me, I can give you a capital N. But we know what the capital N is supposed to be. So take capital N to be equal to, well, if we want it to be an integer, let it be greater than 1 over epsilon. Okay, then the point is then, if N is bigger than big N, then 1 over N is going to be less than 1 over big N, and that's going to be less than epsilon. Big N is bigger than 1 over epsilon, so 1 over big N is less than epsilon. So if N is bigger than big N, we need to show that this bit is true. Okay, so this is the bit we need to show. So for every N, we've stated what our N is going to be, and we have to show that this is true. So let's just write it down. So xn minus pi, remember pi is our candidate limit, that's what we're getting the limit is, so this is going to be the modulus of n pi plus sine n all over n minus pi. So we've done this, we did this already in our rough work, that cancelled with that, so this is equal to the modulus of sine n over the modulus of n. But of course remember, modulus of sine n is always less than or equal to 1, so this is less than or equal to 1 over n. So this is modulus of sine n, much bigger, modulus of sine n is less than or equal to 1. So that's less than or equal to n, but n is bigger than big N, so that's going to be less than 1 over big N, but big N is bigger than 1 over epsilon, so that's going to be less than epsilon. Okay, and we've done everything we needed to do because we've shown that I've given you a big N, in this case it's 1 over epsilon, so that whenever we're past that point, whenever little n is bigger than big N, the nth term in the sequence is less than epsilon distance to the limit point, which is pi in this case. Hence, xn. Okay. So this is the final thing we write out. So we've obliterated all our rough work. The only thing we remembered from our rough work was that, but this is the final solution. So whoops, out of time. So we just need to write this down from our rough work where we calculated what the n was. And this is the thing we actually get in the answer.